Thank you. So I'm Jozsef Varga from Konkoly Observatory, Budapest, and back to observation. So I will present some results from the Very Large Telescope interferometer, which can be used to observe inner disks, or the innermost regions. So here is a motivation. So I'm very much interested how this planet-forming disk look like, and from the last decade, amazing results came up from, for example, from the Sphere and the ALMA observatories that revealed there is a lot of substructure in these disks, and much can be learned about what physical processes can cause these substructures. But the inner disk remains unresolved in these observations. For example, these circles denote the orbit of Jupiter on these pictures. So, as others told before me, that these regions can be resolved with optical infrared interferometry, and I'm using the data of the Very Large Telescope interferometer, and you can see what are the different bands that we can observe with this facility. There are multiple instruments on VLTI, each looking the sky at different wavelengths. And so let's see what are the structures we want to observe with this, for example. First, the resolution. So the resolution with the current baselines goes from about milliarc-second resolution at the near-infrared to around 1 AU, 10 milliarc-second resolution in the N band, and translated to the nearest star-forming regions. This is 0.1 AU at the near-infrared and 1 AU at the mid-infrared. And so the dust inner rim for usual T, Tauri, and Herbig stars is around 0.1 AU with some scatter, also depending on the stellar luminosity. And you can see from this plot that we can resolve the dust inner rim with the near-infrared instruments, but not with the mid-infrared instrument. So why is this all good? That's because if we measure the disk sizes, we will see that at longer wavelengths, the disk size will increase. It's mainly because of the temperature structure of the disk. So at longer wavelengths, we get more flux from the colder outer part of the disk. And so, while in the near-infrared, we practically see the dust inner rim, in the mid-infrared, we can see the dust inner rim and what's behind the dust inner rim. Only caveat that the resolution also gets worse towards the mid-infrared. So at every wavelength, usually we have the situation that we have just barely resolved the disk structure. So what can we do? That's the case for a multi-wavelength analysis. So combine all this data together and come up with a consistent model for a disk. And this is what I'm going to show you now. So this is the case for a Herbig star, HG 144432. And so the first two pictures, these are model images which are fitted to the data. And so these models show that in the near-infrared wavelengths of the Pioneer and Gravity wavelengths, we have a structure which is very compact. We have basically a ring, and which is consistent with the dust sublimation. Now, what do we see in the mid-infrared at 3 and 4 microns? This is fitted to the Matisse data. So what is seen here, that we need a second ring in order to be able to fit the data. And if we go to even longer wavelengths, then we have to realize that even a third ring is needed. So that's an evidence that this disk has substructures in the inner few AU. So these structures, so one is located at, so innermost ring is located at 0.15 AU according to this model, consistent to the dust sublimation. Then the second is 1.3, and the third is 4.1 AU. Plus, minus something, because these models, so all this fitting is somewhat model dependent. But we can do even more, because in the end band we have, so these observations come with spectra. So in the end band we see this nice silicate spectral feature, not just in the single dish flux, but also in the interferometric data. And with the modeling of this data, we can derive the silicate composition of this source. And we also could do more, because we know that there should be not just silicates, but other dust types in this mix of dust that is around these stars. And so we experimented with two kinds of composition, one with carbon grains and the other with iron grains. And we found that the mix with iron grains gave much better fit to the data. So that's evidence for the presence of solid iron grains in this disk. And why is that interesting? That it can be very related to the solar system. So what we see that if we infer the elemental composition of the dust around this nice Cervic star to the solar system inner planets, Mercury and Earth, we see that this composition is an in-between case between that of Mercury and Earth. So this was this case study. In the following, I go for a different topic, so that I want to come back to AG 163296, because this is really an exceptional case. And also this now will focus on the time variable aspect. So again, let's do the magic trick of zooming into the inner disk, and let we see that we observe this object with Matisse, and we see this asymmetric feature that we compared with the older data set of Pioneer, and then we found that it is moving. So yeah, but it's all clear now because we have this new wonderful Chara data set. We also compared the structure which we saw in Matisse with a hydro simulation of a vortex created by Rossby wave instability, and also we found that it can be compatible. Yeah, but now this became much more complicated, this thing, because we have this Chara imaging of this dust clump, and so how this compares to the Matisse observation. One thing that struck us is that this blob orbits at sub-Keplerian speeds 3 times lower rate than what is expected from the Keplerian period. And so let's see. If I compare the blob position, so with the Matisse data, this is another realization of the Matisse data. So as you can see, here we have a ring structure which is smooth on both edges. Here we have a ring structure which is sharp on the inner edge and smooth on the outer. It's from a temperature gradient model. So in that case, the inner radius is just a bit farther out what is found in the Chara data. So that is quite good. But if I calculated the location of the blob from the Chara measurement, I found that in the Matisse epoch, 2019 May, the blob should be here. But we measured it here. So what is not the situation? That's the question. Okay. So, yeah, that's an open issue. But if I may, then I have 2 other nice systems that I would like to mention. One is DXCHA, which is a spectroscopic binary. And my PhD student led a very nice study on this. So the separation of the two stars are around 0.2, 0.3 AU. These are on eccentric orbits. And we observed with Matisse on 3 different epochs. And also this is, again, a data fitting. And what is now evident from these images that the arc, this ring-like arc, is not at the same place. So here, again, we have a case for time variability. And so what is it? The interesting thing about this, that this ring is very close to the stars. And it is not expected because hydrodynamic simulation that is tailored to this object showed that the inner spectroscopic binary should carve a large cavity in the inner disk. But it's, from the mid-infrared data, it's shown that the structure, which we see in the L-band, is much closer to the star. So based on this, we think that it might be that we see these spiral wakes induced by the stellar orbit. And maybe the inner warm part of the spiral wakes can be seen in our data. So, how much time I have left? 1 minute. Okay. So, if you bear me. So, that is the last I would like to show is another Herbig star, which is called TCRA. And this is a sphere image. And we observed with this Matisse, with Matisse. What you see here is that it is an almost a John disk. This is the disk surface, and this dark lane is the midplane. So what we see in L-band, okay, it's very tiny. But there is another component which is hidden in the sphere image. So I think that it's another case. It's not for specifically time variability, just that we can also do these kind of things to recover embedded unseen binary companions with these instruments. So, and the companion located at 23 AU towards the west from this. And also this appears that this has a disk, so, and it's pretty extended. So I will conclude here. So thank you for your attention.
Come on, you haven't exhausted all your questions, have you? Nuria.
Yeah, I just had a question that you had like this composition that you needed like pure iron to fit the 10 micron silicate feature, right? In addition to the silicates. Yeah, and I was wondering but you only showed from 8 to 12 microns. I was wondering what was a shorter wavelength, how good was the fit?
Yeah, for the 8 to 30 microns, so for only N-band, iron is not really needed to fit those data. I can also assume that there is some mid-plane emission, which has an uncharacterized dust, which is featureless, that could be compatible with iron or carbon as well. I may grab some, sorry? This, yeah. So what is the real difference between the two models with the carbon and iron-rich dust? That is this region. So around 6 to 8 micron. So we see that the iron-rich model fits better in this region than the carbon-rich model. And that's the real difference between these two models.
Which curve is the iron? It's the green? Or?
It's not, it's neither of them, because these colored curves shows the dust emission at different radial zones, but for all of the dust, so including iron. So iron plus silicates.
Okay. Yes.
Keeping on this bonus slide here, it kind of looks like the longest wavelength data point is discrepant for both iron and carbon. So do you have any idea as to why that might be?
Yes, this is because there should be an additional, this component should be included in the model. I guess it should be further, so farther than 5 AU. That contributes to this emission around 2040 AU, not 2040 micron.
Thank you.
Luigi.
Yeah. I have a nasty question on the last source that you showed, so the hidden companion one. So,
yeah.
How many embedded binaries, how many embedded companions do you think we are losing in the protoplanetary disk community?
I have no idea.
I think a lot.
This is a bit of a serendipitous. I know maybe 2 more in our data.
Right.
Of like 100.
John, do you have something you want to?
I would just say that for these disks that are very full, I don't think we're missing that many binaries, because usually they would carve a cavity, or they would look like a pre-transition disk or something like this. So, I mean, yes, there are some we're missing, but if you look at the SED carefully, you should see signs of them if it's actually stellar mass.
Could you show TCRA again, the image?
Yeah.
No, go back to the interesting one. Well, I mean, they're both, actually yours is more interesting, but that's a big mess in that environment, isn't it?
Yeah, it's a big mess. And this binary companion was...
where is he?
Here. Where is this spot here? So if I...
So he's...
Yeah, here. So
it's just an infrared source? Just infrared? You can't see it in the optical?
Yeah, infrared. So it cannot be detected in this H-band image.
Uh-huh.
So
okay.
even longer, so
Yeah.
L-band. So it's at 3 micron we could detect it. But it was pressured from earlier spectroastrometric measurements.
Oh. Okay.
They could say that there should be a companion along this line. And now it is confirmed. And also this, so the author of this paper also supported this, that there should be the binary along this line, which drives a cavity in the inner disk, disk warp, and may be responsible for this messy shape, the whole disk.
Okay, thanks. Well, let's thank our speaker again. Oh, no, okay, no. Sierra must be served.
Okay, well, this is a question for you, Jozsef, but also, John. We're seeing these really complex, inner disk structures and these asymmetries and this time variability. And this is really biased towards the brightest objects that we can characterize well. So I understand we may not be able to do this for lower mass objects. But I'm wondering if you expect that this does continue down to the lower mass objects, or is this something that we expect to just be present in the Herbigs?
I would expect that it can be also present in T-Tauri stars. Just really, it is much harder to observe.
Yeah, Herbigs are bright.
Thanks.
Okay, well, let's now thank our speaker again.